is a way to represent connections between objects. This is different from other types of graphs you've encountered in the past, like the graph of a function or graphs like histograms or pie charts. This is a different mathematical object, and so the definition of a graph is that a graph G is a set of vertices, V, and a set of edges, E, such that each edge joins two vertices. Vertices are represented by points. Computer scientists sometimes call vertices nodes. Vertices are represented by points, and edges are represented by line segments between those points. These two vertices are joined by an edge, and I'm just going to leave this vertex by itself. It's not joined by any edges. A graph can be labeled or unlabeled. If we label the vertices, then we could give them any names we wanted. Let's say A, B, C, D, E. So we've just labeled those vertices. And so now our vertex set is the set A, B, C, D, and E. So that's our set of vertices. Now our edge set is the set of pairs of edges between vertices. So AB is an edge, and so I'll write AB. BC is an edge between two vertices. CD is an edge, and DB is also an edge. So that's all of the four edges of this graph. One thing is that because this isn't a directed graph, the order of the vertices doesn't matter. So for example, the edge DB is the same as the edge BD. Graphs can be studied as objects, just abstract objects, but they can also model a variety of applications. For example, we could model a transportation system, so the vertices could be airports, and we could put an edge between two vertices if there's a direct flight between those airports. Or a graph could model a social network, so for example, the vertices of the graph could represent users of Facebook, and we could put an edge between two vertices if those two people are friends. One of my primary research areas is in mathematical chemistry. In mathematical chemistry, vertices represent atoms, and we draw an edge between two atoms if there's a chemical bond between them. For example, these could each be carbon atoms, and we could have chemical bonds between those. And maybe there's actually a double bond between those pairs of carbon atoms, and we could represent that by a second edge. And then we could have hydrogen atoms coming off of each of those carbon atoms. And once we've completed that, then this is now the graph for the molecule benzene. So you've probably seen graphical representations like this in a chemistry class. And actually, this is where the name graph comes from. It comes from the graphical notation for chemistry. I particularly study carbon molecules, and that includes molecules like fullerenes, graphene patches, nanotubes. And I study mathematical properties of the graphs that relate to properties of the molecules like stability and electrical conductivity. Graphs are really useful in computer science. So for example, a binary search tree is a graph. A multigraph is a graph that can have more than one edge between a pair of vertices. So for example, the graph of benzene above is a multigraph because we have two edges between each of those pairs of vertices. So this is a multigraph. Whereas a simple graph is a graph without loops or multiple edges. So this is a simple graph. A loop in a graph is an edge from a vertex to itself. So that would be a loop at the vertex A. So now this is not a simple graph. If we wish, we could also add multiple edges. So we could have maybe 3 different or even 4 different edges between that pair of vertices. 2 vertices are adjacent if they are connected by an edge. So here the 2 vertices x and y are adjacent because they're connected by an edge. We could call that edge xy, or we could call that edge yx, or we could give its own name like E. 2 edges are adjacent if they share a vertex. So, for example, the edge E is adjacent with the edge, let's say, A. So E and A are adjacent edges because they share the vertex Y. An edge and a vertex on that edge are incident with each other. So, for example, A and Y are incident. The degree of a vertex is the number of edges incident to the vertex. So in our example above, the degree of the vertex x, for example, is 2 because x is incident with 2 edges, this one and this one. And the degree of the vertex y is 1, 2, 3, 4, 5. The degree of the vertex y is 5 because y is incident with 5 edges. The degree of the vertex s is 1, and the degree of the vertex L is also 1. They're each just incident with 1 edge. And the degree of the vertex V, the degree of the vertex V is just 0 because V is incident with no edges. There's one caveat to the definition above, which is that a loop contributes 2 to the degree of a vertex. So, for example, the degree of the vertex T above is 1, 2, 3. And a final note on this page, this entire graph is a single graph. So even though it is disconnected, this entire graph G is a single graph. It is disconnected, meaning that we can't get from one vertex to another with a path of vertices that are connected. However, this is a single graph. It's disconnected, and it has 3 components. We'll talk more about connected and disconnected graphs and paths in graphs later on.